This video will focus on using right triangle trigonometry to solve problems involving three-dimensional spaces. Before continuing, make sure you know your trig ratios and can use them to calculate unknown sides and angles in right-angled triangles. The only new skill required is the ability to effectively visualize where the right triangles are when provided with a three-dimensional drawing or, in more difficult cases, a description only. If you struggle with such visualizations, use three-dimensional models, especially clear and hollow models that allow you to draw on the faces or place objects inside to help you see the required angles and triangles. We will cover two examples to illustrate this process. The first example has the diagram provided. The diagram includes the dimensions of the rectangular prism, but we are asked to find the angle between the longest diagonal and the base of the prism, which is not indicated on the diagram. The longest diagonal will go from any top corner to the opposite bottom corner, such as AG, CF, or ED, etc. We will use ED here. The angle we require is between ED and its projection onto the base, which is here, HD, the diagonal of the base. Now we see the triangle we hope to use, triangle EHD. However, we need two sides to calculate an angle, and currently we only know EH. Looking at the base though, we see that its diagonal is the hypotenuse of another right triangle, of which we know two sides. A simple application of Pythagoras' theorem will allow us to determine its length. Labelling the hypotenuse C, we have C squared must equal 5 squared plus 8 squared, which is 89. Finding the square root reveals this undesirable decimal. You should be aware by now that we prefer not to round answers from intermediate calculations to avoid accumulating rounding errors. I will endeavour to address the intricacies of this in another video. In truth, it's usually sufficient to carry a few more decimal places or significant figures than will be required in the final answer. We could write 9.433... for example in our calculations. However, an alternative in a case like this is to leave the answer in surd form. Transcribing this answer to our right triangle, we now have two sides and can calculate the required angle, which I now label with the Greek letter theta. Labelling our sides and using SOHCAHTOA, we see that the tan ratio is required. Tan is opposite over adjacent, so tan of theta must be 6 over the square root of 89. Using inverse tan by pressing the shift and then tan on your calculator, we find the angle to be 32.5 degrees, correct to one decimal place. As always, I will remind you that you should make sure your calculator is correctly set to degrees here, otherwise your answer will be incorrect. Example 2 is slightly more difficult because we need to draw the diagram. We start by drawing a cone shape. We can mark in the provided radius of 12.5 centimeters, and we are told the angle at the apex here is 36.2 degrees. We need to calculate the height of the cone, which is also the height of this right triangle. Due to symmetry, we can halve the angle provided to find that the angle in our triangle is 18.1 degrees, and the base is the same as the radius of the base of the cone. We can label the required height as h or any pronumeral we so desire. Labelling the sides and using SOHCAHTOA, we find that again we are using the tangent ratio. Opposite over adjacent is tan, so 12.5 over h must be tan of 18.1 degrees. With our unknown on the denominator, you should hopefully recall that this leads to a division rather than a multiplication, so h will equal 12.5 divided by tan of 18.1 degrees, giving us this answer on our calculator. The height of this cone is 38.2 centimetres.